There are phenomena in the cosmos that can release, in a fraction of a second, more energy than all the stars in the observable universe combined, all while emitting, paradoxically, absolutely no light into space. And if we are able to say this, it's because, in the wake of these events, the entire planet begins to vibrate. Today, I would like to talk to you about the merging of black holes, events that are visually impossible to see, yet generate waves of incredible power nearby, and capable of making space-time itself ripple by creating gravitational waves. This happened on September 14, 2015 at 9:45. Almost everywhere at the same time, waves of this kind came to cross the Earth on all continents, just like in the oceans, the mountains, the rivers, the volcanoes. Just like the bodies of all living beings suddenly began to oscillate very slightly, crossed by a series of waves passing through them, at the same time altering distances and the flow of time. Absolutely all the matter present on our planet successively contracted, expanded, following the rhythm of the troughs and crests of these strange undulations, which, in the process, without slowing down at all, continued their progression through our solar system, as fast as light does. Then things returned to normal, until it happened again. Because it happened again on December 26, 2015 3 times, in 2016 8 times, in 2017 and so on, and each time. And as our entire planet rippled while the gravitational wave train passed through it. And the space around you, as well as within you, was again, in turn, stretched, compressed, stretched. You, like me, didn't notice or feel anything at all at the time. Because in the days that followed, the entire scientific community and beyond was overcome with emotion. Because detecting these ripples is the careful analysis of the deformations they cause. Not only is this a first, it allows us, if I may say so, to study some of the most energetic phenomena in the universe, to confirm the theory of relativity, and even to measure the speed of gravity. But before we dive deeper into the origin of these strange vibrations, let me say a few words about gravity. You know, that strange thing responsible for the movement of celestial bodies, that makes objects fall, that makes bodies attract each other, but that in no way explains why we fall in love for a long time. The most effective way we have to describe the trajectory of cannonballs, the fall of any object, as well as the movement of planets, has been Newton's laws of universal gravitation. An incredibly effective way to calculate the effects of gravity in almost all everyday situations. But it reaches its limits near extremely massive bodies. And, in fact, it doesn't really explain how all of this actually works. Basically, in the laws of universal attraction, gravity is seen as a force acting at a distance, transmitted, let's say, almost like a miracle between objects. As if a thin and invisible thread connected all things with mass together. And then, in 1915, Einstein came and completely blew up this interpretation. By showing that gravitation is not a force, but the consequence of a shape, the manifestation of the deformation of space-time. Don't go away, you'll see, it's fascinating. In his theory of general relativity, Einstein shows that the dimensions of space and time are intimately linked, that they are part of a whole, a continuum. And if bodies attract each other, it's simply because their mass deforms the fabric, the space-time in which they exist, a fabric that you can, in a way, imagine, stretched by the presence of objects, galaxies, stars, planets, just like a sheet or a trampoline would be by the presence of a bowling ball. The idea is that the greater the mass of the object, the more pronounced the curvature around it is. And it's the effects of these space-time curvatures that create what we feel as gravity. It might seem a bit abstract like this, but this theory of gravitation explains a lot of phenomena that the laws of universal attraction are simply unable to describe. It even predicts the existence of things that no one had observed at the time Einstein formulated it. And among the many strange implications of this theory, there's even one, which tells us that anything with mass, as long as it's moving, must create gravitational waves all around it. And this applies to anything and everything. Drop any object, and its movement should give rise to concentric waves, just like when a stone falls onto the surface of a pond. Except that here, the ripples travel in all directions, in 3 dimensions, and what moves and ripples slightly, it's not matter, but the space-time continuum in which they exist. The problem is that, although the existence of these infinitesimal waves is predicted by theory, in practice, their amplitude is so small that it was long thought they would remain forever inaccessible to measuring instruments. Consider that even gravitational waves emitted by something as close and massive as our Sun are quite incapable of deforming the matter they encounter during their propagation enough to be detected on Earth. So much so that Einstein himself didn't really believe in their possible discovery. But that's without counting on the ingenuity of people of our species and the fact that the universe likes cosmic events. the cataclysmic kind, like the merger of two black holes. Because these phenomena, whose power defies understanding, can produce waves of space-time that, when they pass through our planet, deform the matter they encounter enough for us to be able to detect them today, but also to precisely reconstruct the sequence of events that gave rise to them. Thus, by closely studying the nature of the signal received on September 14, 2015, scientists were able to identify, reveal in the data the signature of a merger of two black holes, each about 30 times the mass of the Sun, and give us access to the very last seconds of their existence, up to the final event, the coalescence, which took place 1.3 billion light-years away. From here, we don't know exactly when this event began. In any case, the pair of black holes orbiting each other gradually began to experience the slow cosmic dance they were engaged in. Gradually accelerated, the process of coming closer could have stretched over millions, maybe even billions of years, during which each member of the pair continuously lost small amounts of energy in the form of gravitational waves, to the point where this ballet gradually turned into a dance of death. Because, as the distance between the two partners dangerously decreases, the speed of their rotation, on the contrary, increases, and the pair find themselves caught in a vicious spiral on their orbit, growing ever more exhausted. Over time, the two compact stars began to emit increasing amounts of gravitational waves and to follow ever closer spiral trajectories. They kept accelerating to the point that, in the final fractions of a second before the collision, they reached staggering rotational speeds of about half the speed of light. And then this macabre dance came to a sudden end when, with an apocalyptic screech, the two stars finally merged, leaving, in place of the now vanished pair, a single black hole whose mass is less than the combined mass of its progenitors. Because during the coalescence process, it is estimated that in just a few dozen milliseconds, a period 10 times shorter than the blink of an eye, a mass equivalent to 3 times that of our Sun was converted into pure energy. Yet, even though this amount of energy released was, for a brief moment, 10 times greater than that produced by all the stars in the observable universe combined, absolutely no light rays were emitted during the event, because this mass that disappeared was completely converted, in the form of intense bursts of gravitational waves that, following the merger, spread out like a shockwave in all directions, in 3 dimensions. Near the cataclysm, these jolts and distortions in the fabric of space-time must have surged with the full force of a tsunami. And then, the waves continued their journey across the universe. And when, 1.3 billion years later, these ripples finally reach Earth, they have lost much of their grandeur. Thus, as they passed through our planet, these waves produced only tiny distortions, not exceeding 10,000ths of a proton's diameter. And to be able to measure such tiny movements, the teams of scientists developed an ingenious device. These 2 impressive facilities, seen here from the sky, allow us to detect the passage of gravitational waves on Earth. One, called LIGO, is in the United States, while the other, Virgo, is in Italy. In these experiments, each consisting of 2 huge vacuum tubes measuring nearly 4 kilometers, the principle is, broadly speaking, always the same at the intersection of the tubes. A powerful laser beam with a carefully designed frequency is split into 2 separate beams. After making about 100 round trips in each of the tunnels, at the ends of which mirrors reflect them, they come back to recombine at the intersection. These lasers make it possible to know, in real time and with unmatched precision, the distances separating the mirrors placed at the ends. And in doing so, when a series of gravitational waves comes to ripple space-time, they manifest themselves by changing the distances traveled by the lasers in each of the tubes. Because the passage of these space-time distortions, literally and repeatedly, very slightly changes the thickness of the mirrors, as well as the lengths of the tunnels. And since their arrangement allows them not to be crossed at exactly the same time by these waves, the lasers traveling through them end up coming out at different times. And it's the cumulative sum of these successive shifts that made it possible to detect the passage on Earth of the last sigh of a pair of black holes in distress. Well, unfortunately, the downside, when you reach a level of sensitivity where you can measure length variations on the order of 100 millionths the size of an atom, is that you constantly have to hunt for the slightest interference and background noise in the collected data. Intuitively, you immediately think of disturbances like earthquakes or graduate students partying in the building next door, but it goes far beyond that. In fact, these detectors are so sensitive that they can just as easily be influenced by the thermal agitation of atoms on the surface of the mirrors, the vibrations produced by the waves of our oceans crashing on the shore hundreds of kilometers away. just like the wind blowing strongly through the trees near the tunnels, whose roots transmit vibrations into the ground. So, it's especially to make sure that the recorded signal really comes from space, and not from a possible flyfart in the next room. That we have several experiments running simultaneously, thousands of kilometers apart from each other. In fact, it's these large distances between the experiments that mean that when gravitational waves pass through our planet, they disturb our detectors with a slight delay, which allows us to estimate their region of origin in the sky. Until recently, to study the cosmos and all the objects that rest on the fabric of space-time in every detail, we only had light rays, radio waves including infrared, visible, ultraviolet, X-rays, or gamma rays. But with the study of gravitational waves, we've literally opened a new window onto the universe. And these tiny space-time distortions have already allowed us to confirm the existence of binary black holes. Systems that we had never directly observed before could, in the future, offer us an even wider range of possibilities. Because gravitational wave astronomy may one day be able to probe the interior of massive stars that have reached the end of their lives. To teach us more about what happens in the light-opaque cores of these stars that collapse in on themselves to become supernovas. Maybe one day we'll even be able to develop experiments sensitive enough to detect the traces left by faint vibration waves coming to us from the primordial universe. A period in history that is currently visually inaccessible to us, because at that time, matter in the universe was so compacted that light rays were unable to travel through it. So one day, we might hope to see it. We need to be able to identify the gravitational waves coming to us from those distant times, because back then, they had no trouble passing through that infernal density. While waiting for the experiments, LIGO and Virgo have been detecting the passage of new gravitational waves almost every month since they began operating. We have been able to identify the wavy signatures of about 10 black hole mergers, a few neutron-star collisions, and even some events involving celestial bodies of unknown origin at that precise moment. Dozens of ripples in space-time, produced by incredibly violent phenomena, will one day travel through the cosmos. Some of them quietly pass through our planet, causing everything on and inside it to oscillate ever so slightly. And I'm willing to bet that if Einstein were alive today, you would see a grin of pleasure appear on his face at the thought that we managed to detect the passage of these waves nearly a century after he predicted their existence. Without imagining that it would be possible one day to shed light on the fact that these waves, predicted by his theory, really do exist in the universe. Today, by giving us access to the tremendous events that gave birth to them, the study of these tiny distortions of space-time allows us to push our physical theories to their very limits. And I imagine once again, Einstein would be happy if he learned that all the data collected are unanimous. General relativity remains solid, like a rock, still perfectly matching the signals collected so far. Some of them have even confirmed that gravitational waves travel through space as fast as light does. Because yes, through these waves, we've been able to measure the incredible speed of gravity, but to explain the reasoning in detail, we'd need to take our time. So I'll save that story for another episode.